following the quantum neural networks, Stefano Mangini from University of Pavia will tell us about how to do variational learning.
Okay, so first of all, hi everyone, and thanks to the organizer for inviting me to give this talk. I would have loved to be there speaking in front of you in person instead of being like a giant face on a screen, but yeah, such is. Okay, I will say networks. I'll start with a brief just introduction to this work. So just a first slide about what is quantum machine learning. So this work lies in the field of quantum machine learning, which is like a fancy name of speaking about various ranges of techniques, which aims to study, let's say, the interplay between quantum computers, techniques using quantum computers and machine learning. So trying to use, for example, classical machine learning techniques to solve problems in quantum physics or quantum computing, as we saw in the previous days, or vice versa. So using quantum computers to optimistically, hopefully, enhance techniques in the classical machine learning setting, let's say. So I'll start with a very brief introduction about the most basic building block of machine learning techniques, in particular the one based on neural networks. So what you see in this slide is the perceptron, is the classical perceptron, which is like a very rude and also very long mathematical model for a biological neuron like we have in our brains. So all perceptron does is it receives some data, some input data, which I denoted by input vector I. This data can arrive from external environment, from previous neurons, for example. So it takes these inputs, it multiplies them with some internal degrees of freedom of the perceptrons, which are called the weights of the neuron, which are parameters which have to be optimized, which have to be tuned to do something. So it performs this inner product between the input vector and the weight vector, and on top of it, it evaluates an activation function, which is, this activation function has to be nonlinear. If it is linear, that's not much power inside this mathematical model. So you have this output, which that's indeed it's made of two steps, performing the inner product and evaluating the activation function. So you have this output and you use it for further computation or passing to, I don't know, future layers in your computation. So you have this perceptron, you stack a lot of perceptron, one on top of each other, one after the other. What you obtain is the standard artificial feedforward or neural network. Did I hear something? No. Okay.
No, continue.
Go on. Okay, great. So this is for in the classical domain, but now basically there was introduced this kind of quantum neural networks. But what are quantum neural networks? Actually, these terms is often refers to a general term, probably more correct term, which are parameterized quantum circuits. So when we speak about quantum neural networks, actually we're speaking about a smaller subset, let's say, of parameterized quantum circuits in the general field of variational quantum algorithms. So how is a quantum neural network generally built? You have some qubits in your quantum computation, your quantum computer. You start your computation by creating a quantum input state. This state, generally, if you're speaking about, for example, machine learning tasks, the aim is to classify, to perform some input data. So, for example, this quantum input state depends on this X value, which is, for example, your data that you're trying to process, to analyze, to classify, to do something. So the first step is to embed your classical information or your quantum data, whatever, in this quantum input state. You take this row of X and you evolve it by means of a repeated structure of unitaries. Generally, when you're speaking of quantum neural networks, these unitaries are made in this way. So you have repeated some layers, some circuit of given depth, consisting of these red box, which are variational gates. So they have some internal degrees of freedoms. You have design goals that you need to modify, to tune in order to do something with your circuit. And this is resembling the standard classical artificial neural network. And then you also have this kind of blue box, which are fixed gates generally, which pumps entanglement inside the circuit. So you have, for example, CNOT gates, so 2-qubit gates, entangling gates, which are fixed. By repeating this structure for a given number of layers, this small L, you obtain your quantum neural network. At the end of the circuit, once you have your input state evolved, you measure some kind of observable at the end of the circuit, for example, measuring all qubits or only a subset of them. And the result, of course, will depend on the actual values for the parameters inside the variational gates, these red gates. So you have these you measure your observable, use your this data to evaluate some kind of loss function, cost function, which is actually encoding the task that you're trying to solve. So you input your task, let's say, to the shape of this cost function. And once you evaluate this cost function, data update in the circuit. And like in a classical neural network, you repeat this loop for a number of times until you get a low enough cost function. So you are good with it and you actually found an optimal solution. So this is the general idea behind quantum neural networks and general variational quantum algorithms. And up to now, we have there was introduced a lot of actually quantum neural networks, quantum machine learning models. Here are a few, for example, the quantum neural networks, which I just introduced, also kernel methods, which we saw last days, and also other structures. In particular, in the following, what I will focus on is this specific model, let's say, which are quantum perceptrons, where the idea is to take the classical perceptron, so that mathematical model, and try to make it quantum. So reproduce the same dynamics of a perceptron, but on a quantum hardware. So this is the quantum circuit, let's say. So I will go now speaking about this neuron model, this quantum neuron model. First of all, let's try to make quantum the McCulloch-Pitts quantum neuron. McCulloch-Pitts neuron is it's like a perceptron, but it accepts and deals with discrete values. So input vector and either a binarized value, so it can be your input weight vector. And so we will take this as a starting point for your model, and we try to make it quantum. So what we can do that is, for example, by introducing these quantum states. These states, as you can see, are made of, we have one for the input vector. So we have a quantum input vector state and also a quantum weight vector state. And these states are made by a very big superposition state of all the states in the computational basis of a system of qubits. Get J's. We load, let's say, the classical data that we wish to analyze. We have this very big superposition state, and the data are loaded in the amplitude in front of this of the computational basis. We can see that, for example, we need, of course, logarithmically many qubits to load this information, this input vector and weight vector into these quantum states. So that we have this quantum state, we can, for example, try to evaluate their inner product. See that it corresponds actually to the scalar product between the input vector and the weight vector. So we managed to reproduce the first step of the dynamic of a perceptron, which is performing the inner product of two values, of input data and some weight data. What we need to do now, so, is to perform some kind of non-linearity, some kind of activation function. We can do that using this kind of circuit. So the details of the mathematics, let's say on the right-hand side slide, but the idea is that you can use this circuit, which has two binaries, this UI and UW. What the red unitary does is it creates the input quantum states, as you can see in the first equation. The second unitary, what it does is, let's say, it creates the weight vector quantum state and also performs the inner product. If you run the circuit and at the end of it you measure all the bits, the number of times you will measure all qubits in the zero state will be proportional, also will be given by the Born's rule. So we will have this inner product between psi w and psi I, which is actually also the scalar product between the input vector and the weight vector, And the nonlinearity will be given by Bond-Sewell, so we will have this modulus square. So in this case, we introduce the nonlinearity in this model by means of measurement, so by measuring all qubits. Alternatively, there is just a small twist to this method, which is often called Compute-Uncompute method, where instead of measuring all qubits at the end of the circuit, we can just X layer as a NOT layer on all qubits and all NOT. In this way, you simply transfer the information stored in the big state of all the qubits just onto, for example, an ancillary qubit. There is no big change in this twist, just that, for example, if you're trying to build a coherent neural network, in this way you just need to transfer, for example, the information stored in one qubit, or also measure only one qubit instead of all the qubits. So this is just a small change, but we will use actually this circuit in the following slide. So what we can do with this kind of neuron, for example, in fact, was having 4-dimensional input, so data, which can be stored in the state of 2 qubits. We could think of arranging this input vector, for example, in this grid, 2x2 images, where each entry of the input vector and also the weight vector denotes the intensity of a pixel. For example, we can think of having a white pixel if the corresponding entry in that square is +1, while a black pixel if it is -1. So the idea is that for some weight vector, which is a diagonal shape, if we quantum state an input which is actually the same of the inner product will be 1, and we will have we call perfect activation of the neuron. In this sense, the neuron recognized the input, which is actually the same of the weight vector. Other cases, for example, in this one, for these two patterns, you will have that their inner product is 0, so we will have no activation of the neuron. So two patterns are actually very distinct. I will also briefly talk about possible generalization, because up to now with discrete values, so plus or minus 1, but actually a plus or minus 1 can be seen as specific cases of a phase of a quantum state. So it is possible to deal also with continuous variable inside this model. Things are changed slightly, so you have this kind of phase encoding because you encode the classical data into a phase state, and the activation function in this case is the one, the red box, which is of course nonlinear and is also slightly complicated, but that's not of importance here. So what you can do, for example, with this continuous generalization is, as before, is to perform I don't know, classification, for example, of grayscale images. So not only black and white, also the shades of gray in between. This was just a possible generalization. So what I will speak about is the central part of this talk, which is the variational learning. Because what we see now, what we saw up to now, is that we have this circuit to implement the quantum problem is both the creation, also the whole circuit as a whole, is actually inefficient in the number of qubits. Because, for example, we can use either two approaches to perform the computation. One is the brute force approach, which works also for both discrete and for the continuous neuron. And what you do in this case is to have this big superposition state of all the states in the computational basis. You target one and you add the corresponding amplitude, corresponding classical data in front of it. Of course, the space of the Hilbert space or quantum Hilbert space grows exponentially with the number of qubits. So in order to actually perform this kind of brute approach, you need an exponential number of steps in the number of qubits. Of course, that's linear in the number of input data on the dimension of the input data, or the weight vector that you are trying to do. Another possible approach is using states, which is just another which still requires roughly the same amount of operation, but this is slightly more efficient because it requires a lower number of multi-qubit scale. But whatever the approach you use, either the hypergraph or the brute force approach, the idea is that this circuit is very difficult to implement because the number of operational gates you need to use on your quantum circuits scales exponentially with the number of qubits. So what can be a possible solution to this is to make, instead of using the exact circuit, for example, the exact brute brute force approach is to find an approximation of it. You do that by using, for example, a variational approximation. The circuit we had before, where you only need to focus on the lightest part, this layer X. So we just sandwich all these two together, and we will now focusing on approximate this GW operation. What is to use kind of this green variation Ansatz, this green variation, which is of course depending on some parameters, some internal parameter theta. And the idea is to find some octangles for which the green gate will be as similar as possible to the blue one. How we can do that? Of course, we can do that by framing this whole problem as an optimization problem. So we will introduce some loss function, which will measure how this with respect to the blue one. And we'll try to optimize the parameters inside these green gates in order to reach a good enough solution, let's say. In particular, notice that the blue gate, of course, depends on a specific weight vector. So we'll do in the following is that we fix a weight vector and we'll try to specifically approximate that unitary. If you change the weight vector inside this blue gate, of course, you will need to perform the training again. So we needed to change also the green gate. In particular, what we did is to study two possible optimization strategies. In fact, we studied two of these. The first one is using a global strategy, and the second one using a local strategy. The idea of the global one is that you have this very big unitary, variational unitary, which acts always on all the qubits in the circuit. And this is done by similarly to a quantum neural, so there are repeated structures of layers, and each layer is given by some single qubit rotation, followed by some entangling operation. In particular, we study two entangling schemes, which is the all-to-all or nearest neighbor entangling scheme, which I'll talk about in the next slide. And so you have this big unitary which always acts on all qubits. You repeat the structure for a given number of times, for a given depth, and you measure all qubits. You measure some loss function, some fidelity, for example, and you update the parameters inside the circuit in order to find a good enough approximation. Another strategy is the local strategy. This, as you can see in the circuit, you have, for example, a unitary which acts on all the qubits in your circuit, and also this one is made by a repeated structure, so variational gates and entangling gates. So you can have this V1 can be repeated sometimes, let's say. At the end of this unitary, you measure just the first qubit, and you evaluate an activation function, a cost function driving the training process of only this first V1, let's say. So what you do is you perform this big unitary on all qubits. You measure only one qubit, optimize this unitary, and once this unitary is sufficiently optimized, what you obtain is that, let's say, the first qubit is now disentangled of the qubits inside the circuit. Once you do this, you can go with the next layer. You have a unitary which is now acting on a smaller subset of qubits. That is the number of qubits minus one. You repeat this process, so you measure only one qubit. You try to disentangle it from the rest of the qubits inside the circuit and go on until no qubits are. So you can see that the main difference between these two approaches is that you have either a global unitaries and a global cost function, or these unitaries which are always another subset of qubits also have this kind of local cost function, which is one qubit. Here are some mathematical pictures.
Hi, Stefano. Sorry.
Here are some technicalities. Yep.
Sorry. So because your internet is tiny bit unstable, maybe you could turn off your camera for now.
Okay. I can do that. Sorry, I hope that this is better. Should I repeat something in here? Okay.
No, after this, it was okay, and then we had like longer pause. So maybe let's try with turned off camera. Sorry. Continue.
Okay, perfect. Sorry. Okay, so we have these two global and local strategy, and this is some technicalities about the variational parts. So the variational gates are given by this single qubit rotation around the epsilon, sigma Pauli epsilon matrix. And we use the two entanglement schemes, which is either an all-to-all entanglement, where each qubit inside the circuit is entangled with all other qubits in the circuit, or a nearest neighbor approach, where it's like on a linked chain of qubits, so each qubit can be entangled only with one, which is nearest to it, and that by means of CNOT gates. So I will go now into the details, the results of this approach. And first of all, let's see how these variational methods compares to the exact implementation. What we see in this graph is that, first of all, we fixed, as I said earlier, we fixed a weight vector, which is this cross shape, which corresponds in a pictorial representation to this cross shaped form in the upper left of the picture. So, and we tried to approximate the corresponding unitary of UW. That means either of a global and a local approach. What we see here is that we generated some randomly patterns, and the three columns with the three colors correspond to the approaches. The main concept about this graph is that you can see the columns are at the same level. So the global and the local approach, these two variational approach, are actually able to learn the unitary UW and are actually able to be optimized and reach the same output activation. So they perform the same. But we go to more in the detail about this approximation. For example, studying how the global approach, in this particular case with the entanglement scheme set to the nearest neighbor one, is optimized. In fact, as I said earlier, we can take this big unitary, the global unitary, and we have multiple layers inside of this unitary. And what we can see is that if you use only one layer, which is the green curve, there is not enough power inside the variational circuit to get a low enough cost function. So if you only need one, if you only use one layer, you won't be able to sufficiently good approximate the UW operation. But of course, if you increase the depth of the circuit, so you have 2 layers or 3 layers, which is the blue curve, you are actually able to approximate the UW, the unitary, the exact circuit, let's say. So we see that, of course, you need to have a deep enough circuit in order to have some expressive power to approximate the target unitary. But while on the global case, we have only, let's say, 1 degree of freedom, which is the depth of the number of repetition of the layers. In the local approach, we have a slightly more freedom. In fact, let's focus on the right-hand side of the slide, where there is the figure of a 2-1-1 structure. In fact, what we have in the local approach is that you can, for example, you start with a unitary, variational unitary acting on all the qubits. And you can have, for example, there a repetition 2 layers, that the biggest unitary. You can go to the next unitary, which is 1 acts for the qubit. And you can choose to have, for example, only 1 repetition of that one. You can go on until no qubits are left. So you can have a different depth for the different unitaries in your local approach. In this case, also for example, a 2-1-1 structure, which is what you see in the x-axis of this graph, it would be given by this kind of circuit. So 2 repetition for the biggest gates, 1 for the all qubits minus 1, and 1 repetition for the remaining 2 qubits. The last qubit always undergoes a general single qubit rotation, which we don't count in this 2-1-1 structure, let's say. So we can now go to the main graph of the slides. What you see, so on the x-axis is the structure, which we explained now. And on top of each column, you see the corresponding circuit depth. So the depth of the circuit to implement that kind of structure. And the 2 different columns denotes either an entangling scheme using the nearest neighbor approach or the all-to-all entangling scheme. What we see, the first, let's say, things that we see is that also for the smaller structure, which is a 1-1-1 structure, the all-to-all approach actually behaves very good. It has a very high fidelity. In this case, the higher, the better. And this is due to the fact that the all-to-all entangling scheme pumps more entanglement inside the circuit. And this actually, we empirically see that this more degree of entanglement goes with some powerful, more flexibility inside this variational approach. But if you also increase the structure, the nearest neighbor entangling schemes also rises in performances. And what we see, for example, is that the 3-2-1 structure, which we call always decreasing structure, actually gives maybe the best trade-off between the depths of the circuit, which are these blue numbers on top of the columns, and the performances, because both the all-to-all entangling scheme and both the nearest neighbor entangling schemes reach higher good enough performances, which are actually very close to 1. So this is also something that we checked, for example, for going to 5 qubits, because this simulation was performed using 4 qubits. And also in that case, the decreasing structure, which was given by a 4-3-2-1 structure, seemed to yield the best trade-off between the circuit depth and performances. So we decided to keep this like a good rule of thumb. So if you're using a local approach, you should go with this always decreasing structure because it gives you a shallow circuit but with good performances. So we will now compare how this global and local approach performs against each other. And what you see in this graph is a simulation performed for different number of qubits. And we studied the mean iteration, the classical optimizer routine that we used to reach a target fidelity, in this case, 95%. What we see is that the global approach seems to scale better with respect to the local one. But this is due to the fact that in the cases we selected, we have the number of parameters inside the global approach scaled like n squared, where n is the number of qubits. In this case, assuming that you have a number of layers, a repetition in the global unitary, which is given by the number of qubits minus 1. If you're using instead the local approach with the assuming the always decreasing structure, which seems to behave the best, we have this kind of scaling. So we have a number n cube parameters. So this explains why the required iteration for the local approach is worse, let's say, with respect to the global one. But apart from this different scaling, what we saw is that both of them are actually able to train and to optimize it and to properly reproduce, approximate the exact circuit. And this is something that was also seen in this paper, which I referenced at the bottom, where they also compared a similar thing. They were studying layer-wise learning, quantum neural networks, and they saw that either using a global training strategy or a layer-wise learning strategy actually gave same results if you are in a noise-free scenario. So you have exact simulation of your quantum circuit. But things actually changes if you introduce some degree of noise. You pump some noise in the circuit. So we studied also the effect of noise. In fact, we introduced...
Hello, sorry. Just to mention, you have last 3 minutes, okay?
I'm done. So yeah, we introduce some noise and with stochastic measurement outcomes. And what you see, just the main important thing, is that for reaching the same final fidelity, which is this roughly 90% for either the local and global approach, which is at the bottom, you now need much fewer iteration, which is 6,000 for the local approach and 10,000 for the global one. So if you introduce noise, the local strategy actually trains much better. It's possible to train it, let's say. But last slide, I promise. So whatever the approach you use, either local, global, all-to-all, nearest neighbor, whatever mix you like, actually all these variational methods scales much better in terms of circuit depth with respect to the exact method. So if you are trying to do these things, you should go with some variational approximation, because it can be fit, for example, in quantum hardware that we have today. So this is just a summary, and so we introduced this variational approximation for a unitary, and we saw that noise actually plays a major role in differentiating different optimization strategies, and the end result is actually very much NISQ friendly because you have shallower circuits that can be run on current hardware. But of course, there's much to do because these were empirical evidence, let's say. It wouldn't be bad to have some theoretical understanding of how the entanglement play roles and stuff like that. So here are the references, and thank you for the attention. Sorry for the internet connection. I hope you understood something.
Thanks a lot. So we have time for one question, maybe. Okay, is there?
Hi. I had a question about the bar plots. I think it was slide 24 or 25.
Mm-hmm. This one?
Yeah.
Okay.
So I'm not sure I'm fully understanding this because if I'm not mistaken, you said that the blue numbers were the number of gates.
Yeah, in the circuit depth of the circuit. So it's not directly the number of gates, but it's the depth of the circuit is defined as the, let's say, the long layers that you have in your circuit, because you can perform, for example, if you have single cube, all of them at the same time. Okay.
Because looking at these, I would say that regardless of the structure, about 22 layers are enough.
Sorry, I didn't understand your question.
Yeah. So
could you?
If we look at the bars where you reach high fidelity, that is closer to 1, I would say that if you have 22 layers for any structure, you should like already reach high fidelity, no? So
that's true. If you see, the numbers on top of the columns, once you reach a circuit depth of roughly 20, let's say, you are in a good enough approximation. You can rise up to 1, essentially to 1 in fidelity above the 3-2-1 structure. So we said, okay, let's try to have the best possible approximation with the lowest depth. And this was the 3-2-1. But as you say, if you are good with having a 95 fidelity, for example, 95% fidelity, you can pick also smaller structures.
Okay, because okay, so that was exactly my concern. No? Like the 2-on-1 with 21 gates seem to be, well, at least from my perspective here, seem to be to provide the same result as the 3-1 with 30 gates. So
that's true. We went to the 5-qubit case, which was, where is it? I had an extra slide for that. Which was this one. You can see here also, for example, this is the same graph as before, only for the nearest neighbor in this case. And you see that increasing the structure to rise up in fidelity. And also in this case, for example, essentially all structure performs pretty good because they're all above 80%. The 4-3-2-1 structure performs quite similarly to the 3-3-2-2 structure. It was just like for, let's say, a rule of thumb, because you can fix a rule and say, okay, if you use a local approach, let's pick the always decreasing structure. It was like a good rule of thumb. We picked that because we could do some numerics, let's say, for bigger circuit instead of finding the best structure for each number of qubits. We always picked, for example, for the simulation with bigger qubits, this assumption of the always decreasing one, because it seemed to reach the highest fidelity in all our tests.
Yeah, okay, thank you.
Okay, thanks a lot. Then let's thank Stefano again.
Thank you.